Hello, everyone. In our next section of probability, we are going to be start. We're going to start looking at uh, two different types of probabilities. So, one thing is make sure that you have gotten through the first section of notes. I noticed in our last chapter, chapter 10, that some people were kind of doing the assignments in just kind of a different order than I had chronologically kind of laid out, which isn't a huge deal, but this is definitely going to be one where before you can really do 1-4 and 1-5, you're going to want to make sure that you've done and understand 1-1 to 1-3. Okay. Um, but let's get started. So the first type of probability that we're going to look at is mutually exclusive events. And what mutually exclusive means, think of the word exclusive like excludes. Um, so two things that are mutually exclusive are when they have no outcomes in common. In other words, these events cannot occur at the same time. So again, when I hear exclusive, I think the word exclude. And so the outcomes of these probabilities exclude each other. Again, they cannot occur at the same time. Okay. Now, one thing that's going to make sure that's going to be helpful just through this whole unit, but especially today, I had on the other day, I had posted in the updates a little probability cheat sheet. And I would recommend that you pull that up just to reference as we go through. Okay. But let's just kind of try to understand this idea of what mutually exclusive means. So I have three examples we're going to talk through. The first one, a card from a deck of 52. Remember, there's always 52 cards in a deck, is a queen or a face card. Okay. One visual that you can try and picture here is this is really a Venn diagram. So, what you want to ask yourself, the question is, are the following mutually exclusive? What you want to ask yourself is, can you draw one card and have it be a queen and a face card? Okay. And again, this is where even if you don't have a lot of knowledge on decks of cards, this is where that cheat sheet is going to help because I broke a lot of this down. And one of the bullet points, you will see that a queen is in fact a face card. The queen has a face on it, and that's what makes it a face card. And so, because one card could be a queen and a face card, then what that means is that these events are not mutually exclusive because they can happen at the same time. Okay. And that's where people kind of get tripped up in this. It's not mutually exclusive because it can happen at the same time. Okay. Let's look at example B, rolling a 5 and an even number on the same die. Okay. So again, when you are looking at that, can you get a 5 and an even number if you were to roll the die just one time? Okay. And if you roll the die one time, a 5 and an even number are two different things. They can't happen at the same time. So, no, they can't happen at the same time, which means that they are mutually exclusive. Okay. And so, again, that's where people kind of get tripped up because we're saying that no, they don't happen at the same time. So then they are mutually exclusive. Or on the first one, yes, they do happen at the same, or they could happen at the same time. So they are not mutually exclusive. Okay. So get this last one, selecting someone in college who is a high school grad or a female. Well, of course, if you're in college, you are automatically a high school graduate. And I guess unless it's only a male college, then this would be maybe an outlier. But otherwise, you can have a high school graduate who is also a female. Okay. So again, because that can happen, these two events, picking a high school grad or a female, are not mutually exclusive because they can happen at the same time. Okay. So that's going to be our first set of examples today, is looking at if things can happen at the same time, how that's going to affect our probability. So we have two kind of formulas here that we are going to use. So if two events A and B, okay, so this is just kind of a general example. If two events A and B are mutually exclusive, then the probability of A or B is the probability of A plus the probability of B. Here's a really easy way to remember this. If you see the word or in the word problem, you are going to add. So or equals addition. Okay. So again, we are looking at two events, finding the probability of two things happening. And if it's an or and they are mutually exclusive, remember, mutually exclusive means that they do not happen at the same time, they exclude each other, then you're going to add those two probabilities together. Okay? If A and B are not mutually exclusive, remember, not mutually exclusive means that they can happen at the same time. Okay? So if A and B, again, those are just two events. If A and B are not mutually exclusive, if they can happen at the same time, then our formula changes a little bit. We're still going to add our probabilities initially, but if they can happen at the same time, then we are going to subtract the probabilities that they both happen at the same time. Okay, and I know that's a little bit confusing, but make sure you just get that little formula in your notes, and then obviously we'll go through a couple examples here, and that will help clarify things. But again, if two events are not mutually exclusive, meaning that they can happen at the same time, then you have to add the probabilities together, but you have to subtract out the overlap. And so let's look at this in terms of a Venn diagram. All right, I'm going to draw two circles here. I'm going to use the red circle to represent the probability of event A, and the blue circle to represent the probability of event B. Okay, and in this scenario, if it's possible for them to happen at the same time, again, think of it like a Venn diagram where there's this overlap in the middle. Okay, so what we need to do if two events are not mutually exclusive is we need to subtract off the overlap. Okay, and the reason why we're subtracting the overlap is because what you're actually doing if you don't subtract is you're counting every possibility that's in the middle here. You're counting those possibilities twice. Okay, and we can't do that. We can only count them once. So then we subtract those out. Let's take a look at what that would look like with an example. All right, so it says a pair of dice is rolled. What is the probability that the sum of the numbers rolled is either a 7 or an 11? Okay, so first thing you want to ask yourself is, are these two events mutually exclusive? So if you roll two die one time, can you roll a 7 and 11? Okay, well, I mean, think about it logically. If you are rolling two die, they can't add to two different numbers, right? If you roll a 3 and a 4, that gives you 7. There's no way that 3 plus 4 can give you 11. If you roll a 5 and a 6, that gives you 11. There's no way that 5 plus 6 can also give you a 7. Okay, so no, these can't happen at the same time. So again, that means that they are mutually exclusive. Okay, and so if they are mutually exclusive, I'm going to go back to our formulas. If they are mutually exclusive, what we're going to do is we're going to add the two probabilities together. Okay, so we're going to find the probability of rolling a 7 or 11 by adding the probability of rolling a 7 plus the probability of rolling an 11. Okay, now again, you should have that Google Doc open, because one of the things that I've added in that Google Doc is how many different possibilities there are when you are rolling two die. Okay, there's a table in there and everything that will be really helpful. And you'll see that there are 36 possibilities for rolling 2 die. Okay, but now what we need to do is we need to figure out how many possibilities are there to roll a 7. All right, so we can get 1 and 6, 6 and 1, 2 and 5, 5 and 2, 3 and 4, 4 and 3. And so that's 1, 2, 3, 4, 5, 6. There are 6 different ways that we could roll a 7. Okay. Now we do the same thing 4 and 11. You could get a 5 or a 6. You could get a 6 and a 5, and that's it. Those are the only 2 ways that you can roll an 11. So then there are 2 different ways that you can get an 11. When you are adding fractions, you add straight across the top, and then you do not add the bottom. You do not add or subtract when you have a denominator. So we get 8 over 36. We should always simplify our fractions. If I divide by 4, the probability that you roll a 7 or 11 is 2 over 9. Okay. Now, again, let's look at this as sort of a Venn diagram. Here's the probability that, or here are all the ways that you could roll a 7 that I just circled in red. Here are all the ways that you could roll an 11 that I just circled in blue. Notice that the middle is empty because, again, you can't have 2 numbers that add to 7 that also add to 11. So that middle part is empty. There's nothing that we need to subtract out. Okay. Let's look at another example. It says a pair of dice is rolled again. What is the probability that the sum of the numbers rolled is either an even number or a multiple of 3? Okay, so first thing we should probably do is just write down our multiples of 3 so that we know what we're looking for. And when you're rolling a die, your biggest sum could be a 12, right? If you get a pair of 6s. So from 3 to 12, there's 3, 6, 9, and 12. Those are the 4 multiples of 3 that you can get when you roll a pair of die. Okay. The other event is rolling an even number. So that's 2, 4, 6, 8, 10, 12. Okay. And what I'm going to do this time is I'm going to start this one with the Venn diagram picture. All right. So let's use red to represent even numbers. All right. And so again, I had 2, 4, 6, 8, 10, and 12. Let's use a blue circle to represent the multiples of 3. I have 3, a 6 again, 9, and then a 12 again. So in this case, again, if I'm looking at that middle part, there's an overlap. And so what that means is that because they can happen at the same time, these events are not mutually exclusive. They can happen at the same time, so they are not mutually exclusive. So what I'm going to have to do is I'm going to have to take the probability of rolling an even number, add it to the probability of rolling a multiple of 3, and then this time I'm going to have to subtract it from the probability of getting an even number and a multiple of 3. Okay, so again, if the 2 events are not mutually exclusive, if they can happen at the same time, then you have to subtract that overlap. Okay, now this problem is going to take quite a bit of side work just because there's a lot of different possibilities that we have to mark down. So let's start. I'm going to be a little bit more organized than I was on the last one. So all the different ways that you could roll a 2 is just by getting a 1 and a 1. Okay, all the different ways that you could roll a 4 is by getting a 1 and a 3 and a 1, and a 2 and a 2. All right, all the different ways I can get a 6 would be a 1 and a 5, 5 and a 1, 4 and 2, 2 and 4, 3 and 3, 8. Oop, can't use a 1 there. 2 and 6 would be the lowest one. 2 and 6, 6 and 2, 3 and 5, 5 and 3, 4 and 4. A 10, 4, 6, 6, 4, 5, 5. And then a 12 is only a 6 and a 6. So these are all the different ways that I can get an even number. Again, I'm actually going to erase that. There are 36 total possibilities when you roll 2 die. And it looks like there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 different ways to get an even number. Okay? If you think about it, if your options are even and odd, that means that half of your rolls have to be an even and half of your rolls would have to be an odd number. So that's why 18 out of 36 makes some sense there. Okay, now I need to do the same thing for the multiples of 3. All right, like I said, this problem takes a little bit of extra side work here. And just to make things easier, okay, I'm going to circle those in red because those are my even ones, and that's what we used before. And then I'm going to write the multiples of 3 in blue. So for 3, I have 1 and 2, 2 and 1. For 6, remember we already wrote those ones on the last one, but just to be thorough here, I'll write them again. For 9, we have 3, 6, 6, 3, 4, 5, 5, 4. And then for 12, again, we just have a 6 and a 6. And so if I count the number of ways we could get a multiple of 3, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 different ways that we could get a multiple of 3. But now I need to multiply or subtract out the probability of getting an even number and a multiple of 3. Because if you notice what we've done is we have counted the 6s and the 12s twice. Okay, and we cannot count those twice, even though they are even and a multiple of 3. All right, so now what we have to do, since we counted them twice, we're going to subtract out the numbers of ways that that can happen. All right, so to roll a 6, it was 1, 2, 3, 4, 5. And then to roll a 12, it was 6. So I need to subtract out 6 over 36 possibilities. Again, when you're adding or subtracting fractions, the denominator should stay the same, and you just add and subtract straight across the top. 18 plus 12 is 30, minus 6 is 24. Let's see, I can divide that by 12 to get a probability of 2/3. So when you roll a pair of die, you have a 2/3 probability that your roll will either be even or a multiple of 3. Okay. Again, you do have a table on your little cheat sheet that I made for you to help you with kind of finding some of these possibilities. But there's not really any way around it. You're just going to have to list out every possibility in order to find the number of ways sometimes. That table should definitely help though. Okay, so again, make sure you just have that Google Doc up when you are working through these problems, as you can reference it and it should be helpful. Our next type of probability today is independent versus dependent. Okay, 2 events are considered independent if the result of one event is not affected by the results of the other events. Okay, if A and B are independent, then the probability of A and B equals the probability of A times the probability of B. And so once again, I'll make this easy for you. If when you read the problem, it says and, then you multiply the probabilities together. So if you see and, that means multiply. Okay. Some phrases that you'll see in your examples to also look out for, other than and or, Some other things to look out for: if two events are independent of each other. A common phrase that you will see is the phrase with replacement. Okay, so it'll be something like you have 10 marbles in a bag and you're going to randomly draw one and replace it. You're going to put it back after you draw it. Okay, something like that. Again, looking for a phrase like with replacement. On the other hand, if we have independent events, then we could also have dependent events, where quite literally the probability of one event depends on the probability of the other. Okay, and so again, it's still an and problem, so you're still going to be multiplying. But in this case, you're going to see a phrase like without replacement. Okay, and again, just a quick example of that would be you're taking marbles from a bag, but if you take out the marble and don't put it back in, you've now changed the total number of marbles in the bag, and so now that changes the probability. So again, quite literally, the probability of you pulling the second marble changes and depends on what happened during the first time you pulled the marble out of the bag. Okay. Again, this will be helpful just to keep an eye on here. When you see the word with replacement, that is, you are going to be finding the probability of two independent events. If you see without replacement, you're going to be calculating the probability of two dependent events. Okay. Those aren't necessarily the only phrases that you will see, but those are definitely the two most common phrases, with or without replacement. Okay. Let's go over an example. So it says a drawer contains 3 red paper clips, 4 green paper clips, and 5 blue paper clips. One paper clip is taken from the drawer and then replaced. Another paper clip is taken from the drawer. What is the probability that the first paper clip is red and the second paper clip is blue? Okay, so let's kind of pull out some of the important information here that we just talked about. First thing is in that second sentence, I see that it says and then replaced. So I'm going to take a paper clip out, but then I'm just going to put it back in the drawer. All right, and like we said when we were trying to determine if it's independent or dependent, if you replace the item, then it is independent. Okay, the two events are independent. All right, I also see the word and, all right, which then indicates we are going to multiply. So when you're reading these word problems for probability, one of the first things I would look for is it an and or an or type of problem? Okay, because then that's going to determine if you add or multiply the probabilities together. Okay, now let's actually get into what probability we're trying to find. It says, what is the probability that the first paperclip is red and the second paperclip is blue? All right, so we're going to find the probability of getting a red, and we're going to multiply it by the probability of drawing a blue paperclip. All right, so in the first sentence, it says the drawer contains 3 red, 4 green, and 5 blue. So that would be a total of 12 paper clips in the drawer. And because we're putting the paper clips back, you're still going to have 12 paper clips to choose from when you select the second paper clip. Okay. In all, there are 3 red paper clips. And again, because you're putting the paper clips back, that's not going to change for your second drawing. So you still have 5 blue paper clips. Okay. Now, when you are multiplying fractions, you do multiply straight across the top and the bottom. So on top, I have 3 times 5 is 15. On the bottom, I have 12 times 12 is 144. Okay, I know that's a little bit of a tougher fraction, but you can actually divide that by 3 to get a probability of 5/48. Now, one thing that you'll notice when we compare, if we were to compare and versus or type of problems, an and scenario is typically going to have a lower probability, because if you need two different things to happen in order for you to reach your goal, that's going to be harder to do than if you need one of two things to happen. Okay, and so that's why you see 5/48. Those aren't very good. That's not a very good probability to select a red and a blue. All right. Now that would change if it was red or blue when you were drawing, but this is red and blue. Let's read the second one. It's actually the same exact problem for comparison's sake, except you'll notice the red there, it is not replaced. So you draw one paper clip and then you just put it off to the side and draw another one. Okay, so this would be an example, since it's without replacement or they're not being replaced. This would be an example of a dependent problem. And honestly, you don't even really need to spend too much time trying to remember what independent and dependent necessarily mean if you can think about these scenarios logically. And here's what I mean by that. So let's find the same, or let's kind of set up the same type of problem, right? It's still an and problem, all right? And so I'm going to take the probability of red and multiply it by the probability of blue. In this case, the probability of red stays the same, 3/12, because it's the first paper clip being drawn, so I haven't done anything. I haven't taken any out yet. But here's where things change. Once I draw that first paper clip, because it's not being replaced, I only have 11 paper clips left. Okay, and so that's why you don't necessarily need to try and memorize the difference between independent and dependent, but just think through these problems logically. If I start with red paper clips and I take one out, then I only have 11, and that's going to change my probability. Now, I still have 5 blue paper clips, so my numerator doesn't change, but just my denominator. Okay, again, multiplying fractions, you multiply straight across the top and straight across the bottom. Always simplify if you can, and this actually does simplify. It divides by 3 again. Get 5/44 as your probability. So you have a slightly better chance if if you're not replacing, and that should make sense, right? If you have less paper clips to choose from the second time, then you have a higher probability of selecting a blue paper clip, which is what you're looking for. Okay, so then you have a slightly better chance to draw those paper clips. Okay. So this was 1.4 and 1.5. I am going to post some additional examples for you to look through as just a kind of a PDF if you want some extra examples. I do want to try to keep the videos on the shorter side of things, but if you're looking for a little bit more practice, check out our folder for today, and you will see some additional examples in there. Okay, have a good day.